All right, so let's start. Just quickly go over what we did last time. So we have these are okay. So that's the main point from last time. So we introduced the inscribed angle theorem. So what does that mean? Well, so first we have the arc PR. So that's a PR here, right? And then we have the inscribed angle, right? Inscribed angle on in PR. That is the angle here. So alpha. So you get one. You can just pick any point from the arc, Q or Q prime or Q prime prime, right? And then the other 2 points will be P and R. So you can get the angle here, alpha, or you can get another point, Q. You can get a beta here, or you can get a third one, theta here, alpha, beta, and gamma. Now, the core thing is that for the three angles, alpha, beta, and gamma, they are all equal. So how do I know they are equal? Then I need a theorem, and this is called the inscribed angle theorem. So the inscribed angle PQR is one half of the measure of the arc PR. So that's how we can prove this. And therefore, it's one half of the POR. Okay. And if we can prove this, then that means the inscribed angle does not depend on the Q we choose. Right? Q can be any point, right, on the circle here. Right? Of course, not inside the PR. It's outside of the PR. Right? So we can. How did I prove this? Where we proved in the following way. We proved that there are two cases, right? The first case is here. So assume that we have the Q is in this way, O is here. Oops, what happened here? I don't. All right, let's see better. So, so the first thing is that I'm going to connect the Q and O, right? In the case that the QO is inside, right, is inside the angle of PQR, then we can do like that, right? So first, I want to figure out that angle 1 is angle 3 and 4. Can you see that? Angle 1 is angle 3 plus angle 4. This is exterior angle theorem, right? That's for here, right? And so that's for the first part here. Wait a second, my pen. Uh, it's not stop working. Let me pair my. I think there something. It's not paired yet. Okay, give me a second. It should be fine. Still not good. Okay, let me go back to the setting here. I think something was wrong with the setting. um, here, pencil connected. Yeah, it's connected here. Apple Pencil. I think it's connected. Okay, let's go back again. It's not working. My pen is not working here. Okay, let's see what happened here. Hmm, interesting. My pen does not work here, but this one works. Yeah. Anyway, so this page does not work. Okay. So, okay. Yeah, it's better. It's working now. Don't know what happened. What happened? It's always like that. Hmm. Okay. Hmm. Anyway, so this page doesn't work here for my pen, but anyway, so let's just move forward. So if you have this part here, I don't know, it's just stop working. That's very interesting. Anyway, so let me try to okay, let's go back to a new different page here. Does that work here? Yeah, this works here. So if I just open a different page, it's working. Anyway, that's okay. Okay. All right. So anyway, so let me so that's what we did for the previous one. Just stop working here. Oh, it's working now. Amazing. I just don't know what's going on here. Okay. Okay. All right. So that's the proof is that first of all, the angle one is the same as angle 3 and 4, right? Why? Where it's just a exterior angle theorem, right? And because this triangle is isosceles triangle, right? OP equals OQ, and then angle 3 is angle 4, right? So we can say that angle 1 is twice of angle 3, right? And similarly, you can prove that angle 2 is twice of angle 5. So if you add angle 1 and 2, that should be the twice of angle 5 and 3. So that's the reason, right? The second case can be proved in a similar way, right? If it's outside, if OQ is outside of the angle, then instead of doing addition, you do the subtraction, right? That's basically the idea. So let's see, how do I get angle 1? That's my angle 1 here, right? That's my angle 1. So my angle 1 is again, my angle 1 is twice of angle 3, right? And then my angle 2 is twice of angle 5. That's the same idea, right? And then you do the subtraction from both sides. That should be fine. Okay. So that's the main idea from last time. Are there any questions? Any question? Very good. So now let's do today. Today I'm going to keep on working from here. So keep that in mind. The inscribed angle is half of the measure of the arc, right? That's the main thing. We need to do that. And therefore, if we have a bunch of inscribed angle inscribed in the same arc, then those inscribed angles should have the same measure. Okay. So let's say today I'm going to give you some corollary of the previous theorem. So let's see. Suppose the first one we're going to do is that is any angle inscribed in a semicircle is 90 degrees. Okay, so I got a semicircle. I get a circle here, and then I have a semicircle here. All right, so let's say AB, and I got a semicircle. And if I have angle inscribed in a semicircle, so that means I'm going to have a C here. I get this. So ACB is such an inscribed angle, right? It's inscribed in a semicircle. Now, this case says that, so if AB is a semicircle, that means that, so angle C must be 90 degree, right? So we prove that the angle ACB is 90 degree. If AB is a diameter, so this is a diameter here. So if AB is a diameter, Then I want to prove the angle C is 90 degrees. Well, how to prove this? Well, to prove this is actually very straightforward. Why? Because of the previous theorem, right? The inscribed angle theorem. So let's see how to prove it. By the inscribed angle theorem, okay, the angle of the ACB is 1/2 of the measure of the AB. Let me just move that here. So AB, maybe you have a D here. So it's just because if I write AB is confused, that mean it's the upper side or it's the lower side, right? It's actually the lower side. So let's say it's a measure of the arc ADB, right? That's the theorem. But what is that? Well, this is half angle. So this is a semicircle. So if this is semicircle, if this is a semicircle, the measure of a semicircle is just 180 degrees, right? The measure of a semicircle. So this is actually 1/2 of the angle of the AOB. This is the O here, and this is 1/2 times 180 degrees, and therefore it's equal to 90 degrees, right? So we are done for this. So it's not bad. It's very easy to prove this, okay? But I'm going to give you a second proof. So that's the first proof. The previous one by using the inscribed angle theorem. That's the first proof. It's very straightforward. But now I'm going to give you a different proof. Suppose we do not have this. Okay. So suppose I don't want to use this, and can I still prove it? Yes, you can still prove it. You can do the following. I'm going to connect the ONC. So I'm going to do the following. Let's see. I'm going to connect. I'm going to connect the OC. Okay, if I connect the OC, then according to the argument that we did last time, right? So suppose OA equals OC, where this is just because they are radians, right? They are radians, right? If they're radians, then we get the isosceles triangle, and therefore the angle ACO is the same as angle A, right? Angle ACO is the same as angle A, just because they are isosceles triangles. It's an isosceles triangle theorem. Isosceles triangle theorem, right? And similarly, if we have the OB equals OC, same reason. So we can have the angle BCO, angle BCO equals angle B, same reason, right? And then I have the two together. You see that? You got the two together. I'm going to add the two together, right? So I'm going to adding them together. The left hand side, ACO plus BCO, that is just the angle of the ACB. The right side is the angle A plus angle B, right? And now I'm done. Why I'm done? Because you have the triangle sum theorem, right? The sum of them. So, but the sum of this plus A plus angle B is 180, right? And then the left hand side, the right hand side are the same. So that implies that the angle ACB must be equal to 90 degrees, right? Everything's okay, right? So I'm a little bit faster, just because this is actually from some previous class, right? So 07 air geometry, right? We did some kind of idea like that, right? We have the isosceles triangle, right? So we can get this, right? So you have two different ways to prove that. One is direct proof from the inscribed angle theorem. Another one, we don't need to use that. Just use the isosceles triangle. Okay, so that's one. And let's see. And something else. Let's see. Okay. Any question? Oh, we have two people. waiting. All right, any question? Very good. So we are the other coronary. Actually, we mentioned that already. The first coronary is here, right? That's the first coronary, right? And then we have the other coronary, like we just mentioned already. So suppose we have the P here, Q, and here, right? We have a Q, PQ, let's say R. I'm gonna use this as my R here. So this is R here, and then maybe this is S here, right? So we have this one and that one, this one and this one here, right? The second coronary will be that the angle of the PQR is the same as the angle of the PSR, right? Why? Well, we just mentioned earlier, because the both angles, they are inscribed angles in the arc of PR, right? So PR is the arc here. So PR is the arc here, right? And then Q, angle Q is the inscribed angle of PR, and angle S is also inscribed angle of PR, and then we are done. So the proof is just that you have the PQR is 1/2 of that measure of the arc. And same theorem again. So this is actually PSR. And therefore we are done, right? And one more, the next one, coronary, is that, let me just use the same picture here. Suppose this is the O, this is the center of the circle, and then I can have this guy here, right? I can have this guy here. So the third coronary will be that the angle PQR is 1/2 of the angle of the POR. Okay, again, this is just a direct theorem, right? Why? Well, just because what is this guy here? This guy is just 1/2 of the PR. That's a definition, right? The measure of the arc equals the measure of the central angle, right? It's a definition. So, so this angle here, PQ, is just 1/2 of the other angle here. It's just 1/2 of the other angle here. Now you can see that. Okay. Just give everyone one more minute. So we have this. All right. So for the rest of the part, we're going to make use of those the theorem and the coronary here. All right. Now, next the one, we'll have some other coronary. We have a bunch of coronary today. So let's see, number 4. Number 4. Well, some book call that as a theorem. I'm going to call that as a coronary because it's actually from the previous theorem. Okay. So let's say we're going to get a circle here, right? So this is a circle. Now, what I want is that I want to get the angle inside this. I want to figure out how big is this angle. Okay, so let's see how big is this angle here. So I get the A here, B here, and P is here, right? And this is A, B, C, and D, right? So I just get the arbitrary angle inside the circle, okay, APB, okay? So I want to figure out the angle of the APB. How do I get the measure of this angle, right? APB. And here the coronary says that I get 1/2 of the arc of the AB plus the arc of the CD. Okay, so let's see. I understand that. The arc of the AB, where's the arc of the AB? The arc of the AB is here. That's the first one here, the arc of the AB. And where's the arc of the CD? The arc of CD is the other one here. So basically, how do I understand the theorem? The theorem says that if you want to have a arbitrary angle inside your circle, the APB. You just make an extension, right? You make an extension of the two sides, and then you cut the circle with two parts. One is the AC, one is the AB arc, the other arc is the CD. And then you're going to have the AB arc and CD arc, add them together and take the average, and that's your measure of the angle inside the circle. Okay, why? Let's try to figure out the why. Okay, give everyone 1 minute. Let's see how to prove this. So we are getting more and more interesting, the result. And we have more and more proof getting involved. So I encourage everyone to think of that, how to prove this. It's just a very, just a small trick. It's not hard at all. Let me give you a suggestion. All right. Suppose I want to connect B and C. So proof, let's connect BC. All right. Do you know how to represent APB? So because of that, I have my APB. I can write that to be angle B and plus angle C. Can you see that? Angle B is here, angle C is here. Well, this is just an exterior angle theorem, right? For any triangle, you get exterior angle. That's the sum of the two remote interior angles. That's from 0,6 geometry, right? Okay. And now, what is the angle B? Where angle B is just an inscribed angle in the arc of CD. So that's 1/2 of the CD. That's for here, right? What is the other one? The other one is the 1/2, where what's the angle of C? Angle C is the inscribed angle of the arc of AB. Can you see that? So that is the arc of the AB. That's the theorem. And then we are done, right? We just move the 1/2 outside. And it's so simple, right? It's just so simple. But this is very, very useful. So for any angle, all right, for any inside angle, for any angle inside the arc, where if it's inscribed angle, I can get that. I can use the arc, it's half of the arc. But if it's completely inside the circle, then I can have the two arcs. I can take the average of the measure of the two arcs, and that's my measure of the angle, right? Can you see that? Very good. So we are done for this, and we got that. And I'm going to give you a different proof, right? So for geometry, I like to have different proof for the same result. So let's see. We have a different proof. So that's the proof one, right? That's the proof one. Now let's try the proof. Let's try to do the proof two. Okay. Well, for the proof two, let me try to connect a difference in here. So I'm going to do the suppose I'm going to connect the other side. So let me connect the AB. So I'm going to work for the angle of the APB in a different way. Okay. So let's see. I'm going to connect the AB, right? I'm going to connect the AB. Now, how do I get my angle? APB. Well, certainly this is 180 degrees, right? Minus the angle of A, right? Minus the angle of A, and minus the angle of, well, I shouldn't use B because it's not the B anymore. So let me use this one, right? So that one will be the angle of the PBA. Does it make sense? So I have 180 degree minus the other two angles, right? Minus the other two angles. Okay. So I can have 180 degrees minus, what's the angle A? Where angle A is just an inscribed angle, right? Again, it's an inscribed angle. So you use the inscribed angle theorem. It's an inscribed angle of the arc of BC. So that means I'm going to subtract the 1/2 of the arc of BC, right? And what's the angle of PBA? I'm looking for that angle. Well, for this angle, it's the same idea, right? It's the same idea. You get this one here, right? This angle is, again, it's an inscribed angle, right? And it's half of the arc of the AD, right? So this guy goes here, right? This guy goes here. Does it make sense? Does it make sense? Right? And now, well, how do I simplify that? Where you get 180 degrees. Well, 180 degrees can be written as half of 360. So let me rewrite that. So let me redo this. Okay. I'm going to just do that 1/2 of 360 degrees, right? So I have the 1/2. So I'm going to move out the O of the 1/2. So that will be 1/2. Let me do that here. 1/2 of 360 degrees minus the BC and minus the AD. All right. Okay. But now, what's the 360 degrees? Well, 360 degrees is just the entire circle, right? That's just the entire circle. So that means I'm going to rewrite 360 in terms of the AB, arc AB, arc BC, arc CD, and arc DA. Does it make sense? That's 360, right? You have the entire circle, right? The arc measure of the entire circle is 360 degrees, right? And then subtract your BC arc, subtract your AD arc. And now we just cancel out this. So let's see, BC cancel with the BC, right? And then AD cancel with the DA, same thing. And so what's left will be the arc of AB plus the arc of CD, and then we are done. Okay. So give everyone 1 more minute. That's getting more and more interesting. Okay. So that's a measure of the angle inside a circle. Okay. How do I do that? It's just you cut you make an extension of the angle, cut the circle in 2 pieces, right? And then the measure of the 2 pieces, you take the average, and that's yours, right? That's your measure of the angle. So that's the inside angle. Now the next coronary, as you can imagine, you can ask where now if the angle P is an inscribed angle, I'm down. If it's completely inside the circle, I'm down. How about it's completely outside of the circle? Okay, we get the next theorem. Okay, so this is number, let's see, number number 5, I think. Okay, number 5. Okay, so assume that you have a circle, right? Again, now I have an outside. I have an angle outside. All right, so this is my P here, right? This is the A here. This is the B here. So I need to figure out the measure of the APB. Everyone understand that, right? I'm talking about outside of angle, an angle outside of the circle. How do I measure that? And this is actually also very cool. So you get you suppose you get a C here and D here. In the previous one, you are going to add the two. You added. You see that for the previous one, you added the 2 parts. Okay, just because the inside angle are big, but the outside angle are actually small. So how small? You're going to take the difference of this. So you're going to do the following. You're going to have the arc of the AB minus the arc of the CD. Can you see that? The AB is outside, is a farther is side, and then the CD is so your angle basically cut cut the circle in two pieces, right? For the previous one, you add the two pieces, you take the average, right? But for this one here, you're taking the difference of the two pieces. You have the AB minus the minus CD, and then you take 1/2. So that is this. Let's see so they are quite similar. Can you see that? The two of them are very similar. The two of them are very similar. The previous one is the addition of the two arcs and divide by 2. Okay, is the average of the two arcs. And this one is the difference of the two arcs and then divide by 2. Okay, divide by 2. So one is the plus, it's for the inside angle, it's a plus. It's for the outside angle, it's a minus. Okay. So how to prove this? It's just similar to the previous proof. Very, very similar. So I want to give everyone a minute. How to prove this. So give everyone a minute. Well, again, we need a hairpin line. So if I draw the hairpin line, I'm pretty sure almost everyone could finish my proof. So here's my hairpin line. I'm gonna connect the B and C. So let's just connect BC. All right, and then you're gonna write your angle P as the difference of the two angles. So your angle P is some angle minus another angle. Okay, can you hear me? What is this? Well, let me call that angle 1, right? And this is angle 2. So how do you represent your angle P in terms of angle 1 and angle 2? Is that angle 1 minus angle 2? Does it make sense? Okay. So what is the theorem? The theorem is the exterior angle theorem, right? Exterior angle theorem. Angle 1 is the exterior angle. So angle 1 is supposed to be angle 2 plus angle P. And therefore, I can write angle P to be the difference of angle 1 and angle 2. And then I'm done. Why I'm done? Because what is angle 1? Angle 1 is the inscribed angle of AB, of the arc of AB, right? What is angle 2? Angle 2 is the inscribed angle of the arc of the CD. And then we are done, right? So what's the idea here? The idea for both of the proof is that it doesn't matter. It's an angle inside the circle or it's an angle outside the circle. I can always represent my angle in terms of either sum or the difference of two inscribed angles, right? I can always change that in terms of inscribed angles. And then I can use the inscribed angle theorem so that to change that into the measure of the arc. Okay. Does it make sense? And the core thing is the following. Okay, the core thing is the following. Okay, I'm gonna give you one more coronary that combine the previous two together. Okay, so let's see. So I'm gonna connect the inside and outside angle together. Let's see how we can do this. Okay, so that's the next coronary, or you can say it's a theorem. Anyway, either it's a coronary or it's a theorem. So let's see, I'm going to do this. Suppose I have a circle. All right, and I'm going to draw outside the angle like the previous picture, right? I get a P here, I get an A here, B here, C here, and D. So I go from my outside angle. And then I get the inside angle by connecting the diagonals. So I'm going to connect the BC and AD. And so you can see that. So one is the inside angle and the other one is the outside angle. And I want to see what's the connection between them. Okay, what's the connection between them? All right, so if you remember the previous two coronaries, can you write down the connection? All right, so let's say, suppose they intersect at the Q here. So I'm going to have the following. The angle AQB. What is the angle AQB? The angle AQB is half of the measure of the arc AB plus the measure of the arc of CD. This is our coronary 4, right? Coronary 4, we get that. And then I can get the coronary 5. Coronary 5 give me the angle of the let's see, AQB, and then I can have the APB, right? I have the APB. That's this one here, and that one is 1/2 times the arc of the AB minus the arc of the CD. Can you see that? Same thing we just did earlier, right? It's coronary 5. So this is a coronary 5. Okay, but now one is AB plus CD, the other one is AB minus CD, and then you can have some idea. How about I'm adding the two of them together? So I'm going to call that to be the first equation, second equation. I'm going to have 1 plus 2. What do I get here? Where if I have 1 plus 2, I have the following. So I get the angle of the AQB plus the angle of the APB, right? So one angle is here, AQB, right? The other one is APB, right? Can you see that? The two angles here. I just marked here. The sum of them, well, for the right-hand side, CD and negative CD, they're cancel out. And the 1/2 of AB and plus another 1/2 of AB. And now I get a half of, I now get the whole thing of the AB, right? Does it make sense? Right? But the cool thing is that the arc of the AB is just the angle of the AOB. That's the definition of the arc, right? That's the definition of the measure of the arc. So that means, suppose this is my circle here. Suppose this is my circle here. So I'm going to have the AO and BO. So that means this angle is the sum of the other two angles. One is inside, one is outside. Okay, that angle is the sum of the other two angles, inside angle, outside angle. If I add them together, the sum is AOB. Okay, that's one thing. The other cool thing is that where if I get from A and 1 and 2, how about I take the difference of this, right? As you can imagine, I can get also something interesting. So if I take the difference of that, then I can get the AQB minus the APB. What's the other side? The same half of the AB cancel with this half of the AB, right? And the half of the CD minus the half of the CD. So that's a positive, the side of the measure of the arc of CD. But what's the measure of the arc of CD? By the same definition, I'm going to have another angle here. That's the central angle. So let me put the central angle here and the other central angle here. And that is my second one here. So that's the angle here. So this angle is actually the difference of the inside and outside angle. So this is the angle of the COD. So here is my another theorem here. Okay, that's interesting. So it's a little bit hard, well, it's not hard, but it's just there are so many steps here, right? So I want to give everyone 1 minute. Let's go over the theorem here. So what I'm talking about here, I have this picture. I have an outside angle. I have the inside angle. How do I connect the outside angle with the inside angle? We say that the sum of the outside and inside angle equals AO, the angle of AOB. The difference of the inside and outside angle is the angle of the COD, right? So that makes the computation very, very easy. All right, just give everyone a minute. It's a little bit complicated. So let's think of that. If you need a reference of the previous two, I just move down a little bit so that you can see the previous two here. Okay, 4, 5, and 6. These are the very interesting. Read that here. Any question? Feel free to ask your questions. Oh, it's one person. Let me get that person here. Okay. All right. So now I'm going to give you a computational problem. So remember that you have those theorem, right? The inside, the outside. The inside angle is the sum of the AB and CD, right? The outside angle is the difference of the AB and CD. I certainly divide by 2. I forgot to say that. Divide by 2. So the first one is the sum of the AB and CD, divide by 2. The second one for the outside angle is the difference of the AB and CD and divide by 2, right? Okay. So remember that, and then let's work on the next problem. The next problem is just a computational problem. So and so let's see. Here's the example. Okay, so let me give you a circle here. All right, and then I'm going to get. Let's see. All right, so you see the picture similar to the previous A, B, C, D, and then P, and then we get a Q here. And assume that this is 20 degrees and this angle is 30 degrees, all right? And I'm going to find the angle of AQB. All right, so what's the angle of AQB? Okay, give everyone a minute. I'm going to give you the previous picture here. There are some result you can use. Okay. What is the AQB? This is Q. QB. So I'm looking for this angle here. Right, I'm looking for this angle. There are many different ways to do it. I can give you two of this. The first way you can do is that how about you use this, right? So you have the inside angle, you have the outside angle here. So as I mentioned earlier, you have the sum of them. You can set up equation. But for this case, you need AB. I don't have the AB here. But you can see the difference of this. So I'm going to use the second part here. Okay. So can you use the second part here? So you get the angle of the AQB minus the angle of the P equals the arc of the CD, right? That's from here, right? This is from here. Okay. Can you use this and to finish your answer? All right. So let's see where everyone understand that. So that's good. And how do I get the measure of the CD? Where the measure of the CD is twice of the measure of the inscribed angle, which is A. That's the inscribed angle theorem, right? This is the inscribed angle theorem, right? So inscribed angle is angle A, is one half of the arc of the CD, and then we are done. Where just because the angle here, right? This minus P is angle P is 30 degree, and the angle A is 20 degrees, so that's equal to 40 degrees, right? And therefore, the angle of AQB is 30 degrees plus 40 degrees. That's equal to 70 degrees, right? So if you remember all of those formulas, then you can get the answer very fast, right? So that's the first one. So first method. So method one. Suppose you remember those formulas, all right? But then you can say, well, some people might say, well, what happens if I don't remember, if I can't remember? If I can't remember the formula, you're still fine. You're still fine. So the second method is that I don't use those formulas. Okay. Suppose I can't remember, right? Especially this one. I can't remember this one. That's not easy. Okay. Well, if you don't remember this, it's okay. So let's see. I'm gonna do in the following way. The second method is that so master two. Okay, master two. First of all, I can say that angle B is the same as angle A. That's equal to 20 degrees, right? Why angle B is also the same as angle A? Because of our coronary 2. Angle B and angle A, they are inscribed angles of the same arc, right? They inscribe to the arc of CD at the same time. And therefore, so this guy must be 20 degrees, right? So I know that this guy is equal to 20 degrees. Does it make sense? Right? This guy 20 degrees. Okay. Or if this guy is equal to 20 degrees, can you tell me what's the angle measure of this guy here? This angle, the angle ACB. So the angle of the ACB, what is this? Well, this is the exterior angle of the triangle of the BCP. So I can write exterior angle is the sum of the angle P plus the angle B. That's the exterior angle theorem, right? It's an exterior angle theorem. So that's equal to 20 degrees plus 30 degrees. That's equal to 50 degrees. Very good. So if this guy is equal to 50 degrees, now can you tell me the angle Q here? Can you tell me this guy here? The angle of the AQB. What is this? Well, this guy is equal to here and plus here. Can you see that? Because this is again the exterior angle theorem, right? So again, the exterior angle theorem. So this AQB is angle A plus angle ACQ. And angle A is 20, angle ACQ is 50, we just mentioned. So the sum of them is equal to 70. So that's still fine, right? You have two different ways to prove this. Okay, so let me give everyone some time. Okay. Okay. Everyone is good? Very good. So let me move on, and I'm going to give you so today we introduce quite a few theorems. And the next one I'm going to do is that let's talk about the tangent. Okay, let's talk about the tangent. So we are going to go to the so move a little bit. So we have the inscribed angle, we have the inside angle, we have the outside angle, right? We did a bunch of them, and now let's talk about the tangent line of a circle. So let's switch topic a little bit. So I'm going to do the tangents. Okay. Well, so let's see. Suppose I have a circle, right? Suppose I have a circle. And then you have a tangent line. So first of all, what's the definition of the tangent line? So the tangent line B here, and this is A here, and this is the circle of O. Okay. Well, the tangent line, so A is a tangent line, means that, so AB is a tangent line of a circle C. What does that mean? Right? We have to have the definition. What do you mean by the tangent line? So can anyone remind me what's called a tangent line? All right. If you want, you can type in the chat. You can type in the chat. So what is a tangent line? Well, how do you understand that? How do you define a tangent line? Anyone know that? Where a tangent line just means that you have a line here, you have a circle here, and you have only one intersection point, right? You have only exactly one intersection point. So what does that mean? So that just means that the AB and the circle of the O have exactly one common point. One common point or intersection point, right? So if you have only one common point, then that's called the tangent line, right? If you have two intersection points, then that's called intersecting, right? Okay, so here I have a theorem here. The first theorem for the intersection, for the tangent line, is that, well, if I have, let's say, AB is a tangent 9 of my circle O. If that's the case, if and only if my angle of the OBA is equal to 90 degrees. Okay, so that should be like this. I'm going to connect this. Okay, let me remove the B here. I'm going to put the B here, right? Okay, so it says that if you get a tangent line, then this angle must be 90 degrees, and vice versa. Okay, so how do I prove this? How do I prove this? All right. Yeah, so someone say that the O angle OBA is 90 degrees, right? But that's not the definition. That's just a theorem. Okay, so good. It's good, but it's not a definition. Right, but not the definition. Okay. So let's see. I want to give everyone some time. Let's see. How do I prove this? Okay, can you prove that? The only thing you know is that the definition is a tangent line, right? A tangent line. If an angle, a line is a tangent line, means that you have a unique intersection point. You don't have two, right? And if that's the case, then the angle OBA must be 90 degrees. Must be 90 degrees. Okay, so let's see how we can do this. And there is some informal proof, which is some people don't agree with that. Informal proof, you can use it by symmetry. So it looks like that, if you look at that picture here, the left side and the right side, they are symmetrical with each other. So if you agree with the symmetry, then you can do that because the angle from the left is the angle from the right. So, but that's informal. Okay, so let's see, it's not exactly correct, but it's understandable, right? So it's an informal proof. Is that informal proof? Okay, it could be like by symmetry. By symmetry, the left side, the right side, they're symmetrical with each other. If they're symmetrical with each other, then we are done because let me call that the other side is C here. The angle of the OBA is the same as the angle of the OBC, and therefore they are equal to 90 degrees because both sum of them is equal to 180, right? So we're at this point we can accept that, but actually it's not it's not a formal proof, right? So if you want to, later on, when you are in the high neighbor competition, if you write a proving this way, that will be considered to be wrong, because what do you mean by symmetry? How do you know they are symmetric, right? It just looks like they're symmetric, but you have to prove it, right? So so I would consider it's informal, right? Now I'm going to give you the correct proof, the formal proof. So let's see, how do you do the formal proof? Let's say, okay. Well, there are actually two directions. There are two directions. The one is that suppose the angle is 90 degrees, and I want to prove it's tangent. Okay, so let's prove that. So I'm going to give you the formal proof without using the symmetry, right? Without using the symmetry, you can't use the symmetry, right? So the formal proof is that let's assume if suppose the angle of the OBA is 90 degrees. Okay, well, if it's 90 degrees, I want to prove that the AB intersect the circle in exactly one point. You don't have any other points. That's what I want to do. Okay, so let's do it. Let's just pick a point C. Okay, I just pick an arbitrary point. So let's pick a point C. Pick a point C arbitrarily. All right, so let's say. So I'm going to pick arbitrary arbitrary point C in the line of the AB, right? You pick any point C here, and you want to show that C is outside of the circle, right? So we want to prove that the C is outside of the circle of O. If you can prove that, then we are done. Why? Because any other points, arbitrary point other than B, right? If you pick any point other than B from the line of the AB, and you can always prove that C is outside the circle, and then we are done, right? Okay, how do you prove that? How do you prove C is outside of the circle? Well, you just need to mention that OC is bigger than the radians, right? So let's try to connect this. So I'm going to connect this. And now I get the right triangle, right? And if you get a right triangle, then the OC must be bigger than OB. And then we are done. Okay, so let me repeat that. So what I want to do is the following. I'm going to make that smaller, right? So that you can see the picture. So I'm going to do that. So if that's the case, well, just because the angle OBC is 90 degree. And so we get a right triangle. We get a right triangle. And if I get a right triangle according to the Pythagoras theorem, right? The OC square is bigger than the OB square, right? Because the OC square is actually sum of the other two squares. So I can just drop one. So I can say OC square is bigger than OB square, right? And that implies that the OC is bigger than OB. But what's OB? OB is the radius of the circle. So if OC is bigger than the radius of the circle, that means C is outside of the circle, right? So this implies that C is outside the circle of O, and then we are done. Because any other point should be always outside of the circle. And B is the only common point of the line AB and the circle, and therefore they are tangent. Okay. So that's tricky, a little bit tricky. All right, give you some time. Does it make sense? I don't have much time. Just have how much time do I have? Just a couple of minutes. Let me do the opposite thing. So I may not be able to write down everything here, but let's just do the opposite thing. So the opposite part is that, well, what happened if, so that's the first part here, right? That's the first part. So that's one way. If I get 90 degree, I can get, that's one direction. The other direction basically says that if this is not 90 degrees, then I can say that AB is not tangent. This is contrapositive, right? Did we cover that? Yeah, I think we covered that in the previous class, right? So if you prove implication, it's equivalent to its contrapositive, right? So let's say if the angle is not the 90 degree, right? Again, if someone don't understand that, not a big deal. It's just a statement in logic. Any implication is equivalent to its contrapositive. Okay. So let's see. How do I finish my proof? Okay. I get a circle here, right? And I have something here. And suppose this angle is not 90 degree. Well, if it's not 90 degree, that means one angle should be bigger than 90 degree. The other angle should be smaller than 90 degree, right? So without loss of generality, let me draw the picture in that way. This is over here. Suppose this is smaller. So this part is smaller. So less than 90 degree. Okay, if it's less than 90 degree, now I'm going to construct a right triangle. How do I construct a right triangle? I just want to go from here. I draw, I'm sorry, the picture is hard to see it. Let me erase that part. Okay, I'm going to draw that. So suppose this is 90 degree. Okay, so this is A here, this is B here, and this is H. And then I got a right triangle. And in this right triangle, OH is smaller than OB. Again, it's a Pythagoras theorem, right? Same as before. But what's the OB? OB is the radians. So if OB is the radians, then that means OH, H is inside the circle of C. And then we are done. Why? Because if you have one guy is inside the circle, then what happened here? It's just intersecting. So it cannot be tangent. And then we are done. Does it make sense? Right. So I didn't write down the detail, but it's okay. So it's okay. Not a, not too bad. Not too bad. Yeah. So let me summarize here. Today we cover lots of theorems, and be very careful. It's a very hard lecture, and I want you to go over all of the theorem and go over lecture. Perhaps you should review the video, right? So just make sure that you understand everything, because if you get lost today, then later on it's very hard for you to catch up. So be very careful and try to go over the lecture and make sure that you understand everything here. Okay, and that's all. So I don't have time now because I have another class immediately after that. Okay, so see you next time. Okay, bye everyone.
Bye.
Thank you. Thank you.
Bye. Thank
No
you.
problem. Bye.